Hi, so this is the 8th lecture for 7600, and we're going to talk more about virtualization. This should be the last of the virtualization for this class. So first I wanted to talk a bit about the model provided by virtualization in reference to, there was one or two questions about nested virtualization in the, on Piazza. So essentially, if you have a guest OS and it has processes in it, the interface that it sees with the hardware is that, certain physical addresses correspond to I/O devices. Certain instructions manipulate, virtual memory and so on. There's, in particular, and also exception handling. So there's a relationship between there's a control register for the exception table, and the addresses that you put in this exception table correspond to functions which execute when those exceptions happen. So this is a pure hardware interface. It's identical to the hardware interface that's seen on a bare machine, or in essence it's the hardware interface that might be seen on some particular machine. It even has a BIOS for Intel architecture when it boots up. Now, in the case of either classic virtualization or binary translation, in both of these cases you have a hypervisor which runs on top of the regular. So if you have the hypervisor, the machine that it runs on top of has the standard user and supervisor instructions, and it also has the address-based, it has the physical address-based I/O and so on. So in fact, you can run this type of virtual machine, you can run multiple levels of virtual machine, because you can have the hardware and this interface here. So if this is the hypervisor, or the virtual machine monitor, whichever you want to call it, the interface here is the same as the interface here. It's using, as I said, it's using supervisor mode and user mode instructions, control registers, and in the supervisor mode it's using the standard control registers and so on. And then it's providing that same interface to the guest OS. And so in fact we can run another instance of the hypervisor, and then we can run a guest OS up here, because the hypervisor, this hypervisor B, is going to see the same interface underneath it as hypervisor A. Granted, that means that when the guest OS makes a system call, it's going to be handled by the lowest level hypervisor, because this is the one that really has access to protected mode, to supervisor mode. It's going to get forwarded up to the next level, which thinks it has access to supervisor mode, which will then forward it to this level. So unless you do, there's an IBM project called Turtles, actually, which I haven't read more than the abstract, but I think they may actually try to make this process more efficient. Certainly it seems that, you know, the interactions may become inefficient as you nest more layers of hypervisor here. Certainly I've run this configuration when I was at VMware because you can use it to debug the hypervisor from within another one. The problem with hardware virtualization, though, is that there the hypervisor sees an interface which is user plus supervisor plus hypervisor modes, and it exports an interface that's user plus supervisor mode. It doesn't virtualize the hardware extensions for virtualization. And so because of that, although you could conceivably run either of these. So if we call this, you know, CV and BT, if we have a hardware hypervisor here, we might be able to run we might be able to run a binary translation hypervisor here, but we can't run a hardware one here because it doesn't see the interface that it needs. The virtual hardware exposed by the hypervisor is just the virtual hardware needed by the guest OS. So, you know, I'll talk a bit more about that model. You've got a guest OS, and what it sees underneath is typically a disk, a network interface, and either console or graphics. The disk interface, if you boot an unmodified operating system, what it will actually see is a range of physical addresses which correspond to a particular type of disk controller. You know, I think one of them is a bus logic something or other. It's a particular model of disk controller which a lot of operating systems have drivers for. Another one that it supports is an IDE disk interface, which just about every operating system supports. So when this guest OS goes to, you know, on startup, it looks in a certain memory area for the for the PCI bus configuration, and as we know, the hypervisor controls, actually provides fake physical addresses to the guest operating system, so it's straightforward for it to take the physical memory area which is supposed to go to PCI and instead interpret it in software. And then one of the things that it finds enumerating that is going to be an IDE interface. And so when it writes to here, it's going to be writing blocks or reading blocks from a virtual disk, not a real disk. The way that gets implemented is typically the hypervisor let's use a simple case where we have, we'll say it's bare metal virtualization. Basically, you have a virtual machine, you have multiple virtual machines, you've got a hypervisor, and it has its own drivers to the disk, to the network, and so on. So the hypervisor is going to have a file system of some sort, and in that file system it'll just create a great big file. If we want a 64 gigabyte disk, it'll create a 64 gigabyte file, and then if we want to write to a block, to the first block of that disk, if the guest OS is trying to write to the first block of its virtual disk, that's actually going to write to the first block in this file here. And then the second virtual machine is going to have its own virtual disk, and when it writes to that virtual disk, it writes to locations in it. So these files could be simply, the simplest version of these files are just really big files, like an ISO file that contains a CD image. It's just the bytes from beginning to end corresponding to the data blocks on that disk. And when the guest OS writes to the various memory locations here, indicating that it's writing a block of data, the hypervisor traps that access and sends and writes it to the corresponding location in the virtual disk file. Another thing that the hypervisor could do is sometimes you'll actually have multiple disks on a virtualized system, and the hypervisor could actually tie one of these disks to one virtual machine and one to another virtual machine. This is something you would only see in a data center or something like that. Usually this virtual machine talks directly to this disk, and this virtual machine talks to this one. Well, actually, you'll see something like that in VMware if you plug a USB key in. When you plug it into your computer, you'll get a pop-up saying, do you want to connect this disk here to your virtual machine or to your regular system? And if you say virtual machine, then it will set up the same sort of mapping. So rather than mounting this, if you're running Windows with a Linux VM and you plug this in and say, I want to connect it to my virtual machine, then that virtual machine will see a new storage device, and its writes will go directly to it. Will go directly through the hypervisor to it. Now, I'll talk a little bit more about virtual disks. Because in fact, this is an area where frequently you get a lot of multiple levels of indirection in a virtual system. If you've used VMware or VirtualBox, you may have seen the idea of snapshots and also sparse virtual disks. So, as I mentioned, typically a virtual disk is stored by the hypervisor as a file, and that file can either be, we could say a raw file, so that just means that it contains 0 up through n-1 blocks. You allocate all of those blocks on startup, and each of them has and then when it writes, it goes. So you pre-allocate all the data. Now a sparse disk has a map at the front And then the first time that say the first write we want to have is to this chunk here, which is, say, chunk 5, then the map gets updated to say, 5 goes to this first block here. We essentially do something like virtual memory, where we have a map indicating where each chunk of disk can be found in the image. And this means that we can start with a very small disk image but still have a large maximum size. We can say, give this virtual machine a 256 gigabyte disk image, but after we install the OS and the applications, we might only be using 5 gigabytes or something like that. And in fact, this will have only grown to somewhere around 5 gigabytes. Typically, these chunks might be a megabyte, 5 megabytes, some amount, or 4 megabytes, something like that. And what this allows us to do as well is to create a snapshot by using copy on write. So if we want to preserve the state of the disk, we can make a copy of this map and then whenever we are going to modify one of these, we make a copy of it. And so that way it uses, and then at some point in the future we can take another snapshot. So essentially we're able to keep multiple versions of the state of that virtual machine by keeping a copy of this map and making sure that after a snapshot operation we do copy on write to any modified data. And so our new map is going to have pointers to old data that hasn't been modified and pointers to new data that has been modified. And then if we take a snapshot, install a bunch of stuff, find out that it doesn't work, we can roll back to the previous snapshot. This mechanism can also be, so this can be used for, so this allows snapshots, where essentially a snapshot saves a copy of the disk image at a point in time, except that here we're doing the saving lazily by using copy on write. Rather than actually making a copy of the whole thing, we make copies bit by bit as writes come in that would have modified it. We can use these snapshots, for instance, to roll back to a previous configuration. Another thing we can use it for is for instance, to have a master image. So if we want to run multiple virtual machines that are each a copy of that each start with the same configuration, we can have multiple virtual disks all pointing to the same starting image, and then any writes don't modify the starting image, they instead modify these separate sparse images, and through copy on write. Much like copy on write got used in virtual memory. And so here you'll find that this single image captures all the shared data that doesn't have to get modified, all the program installations, things like that, all your man pages, and whereas the actual activity on each virtual machine creates copies of the corresponding segments. we'll see, a ways farther into the semester, we'll see ways of doing this at the file system level, but here we're doing this at the raw disk level. We're splitting up our disk image into these chunks, like I said, maybe they're a megabyte in size or something. They're large enough so that that fragmenting the disk at that level wouldn't significantly impair performance, which actually means nowadays they need to be more than a megabyte. 4 megabytes would probably be a better value. And we allocate in those chunks, we do copy and write on those chunks in order to, if we've taken a snapshot. So these are virtual disks. As I said, you interface to these virtual disks through a virtual I/O adapter. Once you write to that, once the guest OS writes to that guest OS, sends to, its own, what it sees as disk 1, block number, B, count N. So this is some amount of data. This goes into the hypervisor, and it now goes into, software saying, write and we know which virtual machine it is. Here's the data, here's the offset and length. Here it's pure software, and it translates it into an operation on possibly the raw device or some species of virtual disk file. And if it's one of the more complex virtual disk formats, then it may have to do a copy if this was a write, because you have copy on write in these formats. But to the guest OS, it looks like a disk drive. You save data, you can read it back. You don't, roll back snapshots while the guest OS is running. Instead, you shut down the virtual machine, you roll this back, and you boot it up again. Okay, so that's virtual disks. Then the idea of a virtual network interface is similar. Typically for server virtualization, what you'll do is, okay, again, the guest OS thinks that it's talking to an Ethernet. When in fact what it's doing is, it's talking to some send packet function within the hypervisor. What you'll do in server virtualization is essentially you'll give each virtual machine its own Ethernet address. Each of these has its own 48, each Ethernet card has its own 48-bit address, which is used to identify it on the network. And so you give each virtual machine any packets. When the guest OS asks the Ethernet card, what's your address? It responds with this. When this guest OS asks what's your address, it gets this other address. And then when you send packets, these both go out on the wire. When a packet comes in, we look at the address and we send it to the appropriate virtual machine according to its address. So this really looks like we just have an Ethernet switch with a few ports on it, and each guest OS is sitting on a separate port on that Ethernet switch. The difference between, if these were running on the bare machine, we'd have an Ethernet cable here. We'd have a hardware box that said Linksys or something on it, and that it would be plugging into. Here, the guest OSs are running on a virtualized system. This connection here is being done through software in the hypervisor, and software in the hypervisor is doing the same function the switch would do of saying, we have a packet coming in, should we send it here or here based on its address. Now for a hosted virtual machine, it may be a bit more complicated because frequently you don't want to have, because this in fact requires, if this is the box with all the virtual machines on it, it's in fact, when it connects to the network, it's going to have 3 different Ethernet addresses. It's going to have 3 different IP addresses, and so on, just as if it was plugged in. For running on your laptop over wireless, for instance, typically what gets emulated in software is something like your home router, which is doing address translation and so on, but we don't need to go into that much. It's easier to look at the case here where we just give each one a separate Ethernet address. It acquires its own IP address in the same way as it would if it was hooked up here, because the packets travel in exactly the same way. Now, I think I should talk some about the difference between hosted and and bare metal or server virtualization. So it's easy to talk about the case where we've got a hypervisor, we've got the hardware, and then we've got multiple virtual machines. This is a model very much like what you see, it's like the OS model. You have an interface here, which looks like the interface here between the hypervisor and the hardware. The hypervisor controls all the resources of the machine. It has the actual hardware drivers in it, and so on. This works great in the machine room. In fact, Xevious, where your Git repository is located, is a virtual machine on a VMware ESX hypervisor somewhere in CCIS's machine closet, or machine room. But if you run VMware or VirtualBox on your laptop or desktop system, it's somewhat different, because you've got your hardware and you have the host OS running with applications on top of it, And we also have to have the hypervisor running with a guest OS and applications. So how do we do this? Well, a couple things. First, we install a hardware driver on the host OS. So what this does is it gives it gives access to supervisor mode, and thus the raw hardware. So, and then we have the virtual machine manager application, and that runs as a process on the host OS, but what it in fact does is it calls into that driver, it replaces the exception handlers, it replaces the exception handlers, the page table, and so on, and it starts running the hypervisor. Now, when an exception comes in, that exception is going to be for the host. Many times it's going to be for the host OS, whether it's for the a network packet coming in, an interrupt or something like that. So we end up breaking out of the hypervisor and doing what at least VMware calls a world switch, which basically means we switch everything back to the way it used to be. We pretend that nothing happened and that we were just a regular application, and we send, and then we have the driver send that exception back to the guest OS, to the host OS. So we do a bunch of shuffling back and forth between running in hypervisor mode, having a hypervisor running while the actual virtual machine is executing. And by that I mean when it's actually executing instructions. We're talking for very, this is happening at a high frequency. And then when an exception comes in, the hypervisor looks at it and says, is this a page fault? Okay, if it's a page fault, it's for the currently running system, so that's the virtual machine. It's going to be handled in the hypervisor and then forwarded to the guest OS. But say it's a network card interrupt, well, that needs to be handled by the host OS. So it switches back, it undoes what it did to go into hypervisor mode, it restores the CPU state back to what it would be if it was a regular program, and it sends the exception off to the host OS. And then the host OS might switch to another process, which is fine because essentially we're going back and forth between, if we have time going this way, we're executing some host process, we do a context switch into our virtual machine, into the host's view of what the virtual machine process is. And this actually uses the driver to switch into virtual machine mode and run our virtual machine. At this point, we get some sort of exception. And we switch back. So here we switch things like CR3, the page tables. We put in handlers. You know, we installed our own exception handlers. Well, in fact, I believe what you do is there's some control register which points to the exception handlers. So we set that control register to point to the hypervisor exception handlers. Here, we undo all that. We set CR3 back to, you know, the host one. We set whatever this control register is to point to the host exception handlers. And then we let the host, and so now at this point we're running as a regular process, and we let this exception go back to the host OS, which handles it and may, you know, spend some time before it comes back and switches to the virtual machine process again. So we have two things going on here. We have the host view where we have this process, which is, you know, the virtual machine process, but unbeknownst to the host OS, while this process is running, we actually do horrible things with the machine, and we set it to be running in this hypervisor mode until we take an exception and we exit back. And since the host OS isn't actually running during this period of time, it's instead normally it would have been directly executing a program. In this case, it's directly executing our virtual machine monitor and our guest OS. The host sees nothing wrong because although we we switched out a whole bunch of state that the host OS relies on when we made this transition, we switch it all back here. Of course, that means that this switch is kind of expensive, but that's how it works. And then typically we'll also have something. This process won't just be a dummy process. It'll also have the mechanism in it to read and write our virtual disk and our virtual network. So if the guest OS, tried to write to the disk here, that would cause the hypervisor to stash some information away somewhere and exit out of the hypervisor and back to this host, this process in the host OS, basically sending it a message saying, take this data somewhere and write it to our virtual disk image, or I want you to read this section from the virtual disk image, or send a packet on a virtual network, and so on. So we have this communication back and forth between the hypervisor running in its own CPU state with a host OS process which is implementing the I/O for the virtual machine, and also pretending to be a normal process for the host OS. So whenever the host OS sees this process, it's running the this top level process. And then in between, when it's gotten a chunk of CPU time, it transitions over to the hypervisor and runs that. So this is our hosted virtual machine monitor. It turns out that even in the server case, it may do something like this for I/O. In particular for Xen, it essentially dedicates a single virtual machine for I/O, and so there you'll basically save a message somewhere and then transition to what they call domain 0, virtual machine 0, which that's the virtual machine which handles all the I/O, and that will see that a message was posted for it, and it'll actually do the I/O. Or it'll do the virtualized I/O by translating it to a real network or file operation. And so this is how you're able to have a virtual machine running as a process on the guest, because while it's running, it uses this driver in kernel mode, which it installed earlier, to switch, to go into supervisor mode and then change everything, change into the state where it's running the hypervisor. Now, someone mentioned, why can't a virtual machine, why can't a guest OS run just on top of the OS? Doesn't the OS provide the illusion of an actual machine? And the answer is because it doesn't. So if you look at what the hardware provides, we have at this interface we have physical memory, we have address translation hardware, we've got I/O devices which you control by reading and writing, so the interface to the address translation hardware is through control registers. We have exceptions. This is a control register interface, so it's supervisor instructions, supervisor mode instructions, and physical memory, supervisor instructions and physical memory. Here these are physical addresses. And so this is the interface that the guest OS sees, or that an operating system sees. Whereas a typical OS, the interface it provides is a system call interface. So open, close, socket, send, receive. You don't have malloc at the syscall level. You have, for instance, mmap, to allocate memory. But this is a much higher level interface, and it's controlled by executing, basically through system calls. EAX equals, the system call number, and then we do a trap, and that goes into the kernel, and it performs one of these functions. So the case I mentioned of user mode Linux, user mode Linux is a case where someone looked at this interface and said, can I write an OS that runs on top of this. And that is, in fact, so this is an OS that runs on top of the syscall interface. It's complicated and slow. It turned out user mode Linux was a useful thing, so they've added support into the operating system to be able to run it more efficiently. But it, it's not, it in fact is a very specialized operating system. It's far more modified than the paravirtualization used in Xen, and it's more, this is, well, it's like they say, it's like the talking dog. You don't ask, the interesting thing isn't how well it talks, it's that it talks at all. It's some old joke, I guess, from a circus act. But here, it's, it's surprising enough that you're able to run an operating system on top of an interface that was designed for application programs. You're certainly not going to be able to run a general purpose operating system on top of it. Now, another thing that was mentioned is by several people in Piazza is live migration. So this is actually one of the more interesting applications of virtual machines. It grows out of work that was done years ago. There was work at Stanford by Greg Cheriton in what was called the V system on process migration. There was some earlier work, but this is was the first, I think, really efficient one. So migrating processes between different machines. And there continued to be work. There's a very good survey, possibly in the early 90s, by Douglas and someone else, which covered all the mechanisms proposed to date and then said, when is anybody actually going to use this? And it turns out that process migration is hard because you have a lot of state that is really local to the particular machine. However, if we look at a virtual machine, its state, it has a virtual disk, it has a virtual network interface, it may have a virtual display, although for a server that's, rarely used. And if this is our hardware, well, the virtual network interface clearly goes off onto the net. The virtual disk, we could actually store that on a remote, say we stored that on an NFS server, then we can in fact, you could imagine if you were to stop this virtual machine from executing, you were to copy all of its memory and CPU state to another machine, you were to connect the virtual disk to the same file on the NFS server, and finally, this virtual network device has a certain Ethernet address. We could take that Ethernet address and put it over here, and then we start executing the virtual machine here, and it's been migrated. And so the reason, so the theoretical work on how you could migrate a process from one place to another was done under, an OS and process model, but it turned out to be far more useful migrating virtual machines because they have this much simpler interface underneath, so that as long as you're storing the virtual disk somewhere on the network interface moves, and the way network switches work, it will look to the network switch as if essentially you unplugged the cable from here and you plugged it in here, when in fact what you did is you stopped the virtual machine here and you started it up here. If this is your Ethernet switch. So this sees what looks like just a cable movement from one port to another. It adapts quickly, and so because we have this very low-level interface, we're able to migrate a virtual machine from one server to another. Now it turns out that the biggest issue in doing this is we want to do it quickly, and there's a lot of memory to copy. So once again we use a form of copy on write. We essentially do what they call pre-copy. While the machine is running, you copy all its memory from the source to the destination, and you write protect these pages, or you use the dirty bit so that you can keep track of what pages get modified, and you basically pre-copy several times, each time only copying the pages that have changed since the previous copy. And finally you get to the point where there's some small core working set that's still being modified. At this point you stop the virtual machine, you move the last of the memory across, you move the CPU state, the register contents and so on across, and then you start this one up. And it turns out that you can do this in such a way that the downtime is measured in milliseconds rather than seconds, even if the entire copy process may take minutes. So you can, for instance, migrate a web server while the system is up and running and serving requests. Now, clearly it helps if the two pieces of hardware are very similar. In particular, the destination hardware has to be able to support all the features that the hypervisor was providing on the source side, but that's usually not a significant problem. Partly, if you're going to be doing this, you may hide advanced features on this system and only tell the virtual machine that you have a very generic system. And so, this can be very useful in a data center. In particular, it means that a virtual machine, can basically live forever. There's no reason for this virtual machine to go down unless you need to reboot for an upgrade of the guest OS, for instance. If I want to replace this hardware, I can migrate the virtual machine to another piece of hardware and replace this. If I want to update the hypervisor here, I can migrate the virtual machine over, update the hypervisor, migrate the virtual machine back. If I need to move all of the hardware out of one room into another one, migrate something off of one machine, put that in the new room, migrate back, and so on. And so essentially, this gives you, total flexibility to work on your hardware separately from your virtual machines. The next thing we'll talk about is logging and replay. So one of the more interesting things that a virtual machine lets you do is have deterministic replay of of machine execution. So in particular, if you have a virtual machine, all of its, every exception, every I/O request, and so on, goes through the hypervisor. And if we can record the exact time at which each of these happen and the data that was carried in these I/O requests, for instance, then we can basically create a log of this information, and then we can take, and so here this is actually going back and forth from real hardware. Now we can take another virtual machine, and the hypervisor can replay this log and cause this second virtual machine to precisely replay the execution of the first one. And the key to that is to actually make sure that not only does each I/O get the same, the exact same results and so on, but to ensure that the exceptions get delivered to the guest operating system at exactly the same time. So in particular, if a certain exception was delivered between these two instructions on the original execution, we want to make sure that on replay that exception is delivered between exactly those same instructions. And so sort of by construction you can show that if each asynchronous exception is delivered at the same point in the instruction execution on each system, and each read from external hardware emulated hardware returns the same value, and we begin with the same virtual machine memory state in both cases, then the execution of these two machines is going to track exactly. This lets us do a number of interesting things, like for debugging, for instance, it means you can back up and re-execute something multiple times. You can't execute a system backwards normally, not even in emulation, because you don't know, because the operations of a computer aren't reversible. So for instance, you could have two instructions in different places that jump to the same destination. So when you're in that destination, you don't know how you got there. But what you can do is you can, if you can roll back to a previous point in time and then replay, then you can go backwards by rolling back 1,000 instructions and then executing 999 instructions forward, for instance. It turns out there's a fair amount of subtlety to how you can efficiently deliver these exceptions at exactly the same point in the execution. And it turns out you do it using some of the statistics registers that modern CPUs provide. In particular, we use the branch counter, because if you think about it, well, if you've had a compiler course, for instance, you're familiar with the idea of a basic block, where essentially a basic block is a sequence of instructions without jumps in the middle, and without any jumps into the middle of that block. And you can break a program down into these basic blocks, you know, and at some point it may, you know, jump to the beginning of another basic block and so on. But if we can record, you know, how if we can use this branch counter as a timer to say that, you know, an exception was delivered at, you know, branch counter n and then address x. And so what we do on playback is we can set this to cause an exception. So we say, you know, stop when branch counter equals n, and so it will execute at full speed until the branch counter hits n, at which point we'll take an exception and we'll jump to the hypervisor, and then at that point we basically single step until we get to this address x. And that allows us to deliver the exception precisely. These basic blocks tend to be short, you know, a few instructions to a dozen instructions or something in most code, I believe. So, so this process is very efficient, and you should be able to see that, you know, unlike, for instance, setting a breakpoint at a particular address, well, in particular, this avoids some other difficulties, because due to cache timing and so on, it may take cache effects, it may take a different number of cycles to get to the same point in the instruction execution, so on. But if two executions start at the same address with the same value in the branch counter, then, you know, and so we have if we start executing at address A, and we get to a point where branch counter is n2 and address equals x, then if we go to the point where branch counter is n2 and address equals x, here we'll be at the same, we'll have executed the same instructions here. Because here we've executed with no exceptions, so the execution is only going to be determined by the memory contents or anything it reads from the simulated hardware, and that'll be identical in both cases. And so, you know, at this point in time, they've both executed the same number of branches, so they've executed the same instruction stream, and then we step past it to this address, but we haven't gone to another jump, so we know that the first time we hit this address is, you know, we're at the same point in both. this can be used for a number of different things. It can let you have, server 1, and then we can actually send the log in real time and re-execute it on server 2, where this is on-site and this is an off-site backup. So we can use this for live backup. Of course, we may have to slow this machine down sometimes if we can't send the log over quick enough. As I mentioned, we can do it for debugging. In fact, there's been some work I forget how you spell his name, Accountable Virtual Machines, where you can actually, when you save this log, you can cryptographically authenticate it so that someone else can verify that you executed that you executed the right program. So in particular, the usage of this was to validate computer games. So if someone wins a multiplayer game, they send this log to someone else who re-executes it with a known good copy of the program, a version of the program that's known not to have any cheats in it, and if it's able to re-execute this, then we know that it was executed on a legitimate copy of the original program. And this authentication or signing of this is done in such a way that it shouldn't be possible, it should be cryptographically hard to have a different program produce the same inputs and outputs and produce the same signed log of its execution. So that's sort of a an unusual application for this, although I guess less unusual than you might think, given that there's some places like Korea where some of these games are played for significant cash prizes. It's also worth pointing out that this is uniprocessor only. Any of these logging and replay mechanisms work only for uniprocessors because there's a lot of asynchrony down in the hardware level, and that's affected by the execution of the hypervisor during periods of time that aren't visible to the guest OS. We're able to emulate the precise, the reason we're able to replay accurately is because all the asynchronous inputs to the guest OS in this case are controlled by the hypervisor. In the case of a multi-core system, SMP, when you're actually in direct execution, we have asynchronous events, we have asynchrony between the two CPUs, and so in one execution this might set a location in memory before CPU 2 does, or this might, and which one goes first is going to be affected by a bunch of things, including cache state that might have been perturbed by the hypervisor. So there's no simple way to execute, to do logging and replay, precise replay in the same way on an SMP machine. It's an active area of research to see to what extent you can do logging and deterministic replay on SMP systems. You'll see papers on that topic in most systems conferences nowadays. Now, I wanted to go back and cover a couple of things that have been asked in Piazza. So, paravirtualization. Now, I mentioned how, in this lecture I mentioned how user mode Linux runs on top of unmodified Linux. So that's an extreme level of paravirtualization where their requirement was, in fact, that they could modify the guest OS as much as they wanted to. The constraint was they couldn't modify what was in effect the hypervisor. For something like Xen, you want to minimally modify the guest OS and have the hypervisor provide facilities that are very similar to what the hardware provides, except done via a system call interface. It turns out that it is fairly commonly used. In particular, most Unix distributions out there now, I believe, at least Ubuntu, for instance, they're compiled with to detect several different types of hardware, and one of the things they check for on startup is whether they're running on a paravirtualized system. There's a particular, I'm not exactly sure what the hypercall interface is, but it's some trap or illegal instruction, and they run that on startup and check to see whether there's a hypervisor underneath them, and if so, it will run paravirtualized page tables and I/O and so on, rather than running on normal using the normal hardware. You'll see, as I've mentioned, Amazon EC2 uses paravirtualization. Again, I believe that they do so because of efficiency. It does seem to be significantly more efficient than even hardware-supported virtualization. There were some questions about software versus hardware TLB. So the hardware TLB is obviously, that holds the translation between the real page table, the translations that come from the real page table, that gets flushed every time we change address spaces. This may have, a few hundred entries, 200, 500 entries. Filling the page table, each miss here is quite quick. It takes, it may take, dozens, some number of dozens of cycles to handle a TLB miss, but it's not a huge amount. However, and then we have at the top the guest OS, fake page tables. Those are the ones that the guest OS thinks are the real page tables. And in the middle, we have the hypervisor real page tables, which are a translation of the guest OS page tables. So the simplest approach is every time we switch address spaces, every time we switch, we just invalidate the hardware TLB. In fact, you can't do otherwise on an Intel CPU. When you change CR3, it throws out the contents of the TLB. We could do the same thing in the hypervisor. We could throw away the contents of this set of page tables here every time we switch address spaces. The problem with that is that this is much larger. This may be thousands of entries. Filling each entry takes much more time. Each miss here is much more expensive than it is in the TLB, where this executes in the amount of, as I said, dozens, maybe 100 cycles or something. Here it's likely to take 1,000 cycles or thousands of cycles for each miss here. So if we were to discard it on context switch, then everything would be nice and easy. We can just translate on demand from the guest page table whenever we get a page fault. If there's no translation there, we pass the page fault up to the guest. So that's nice, simple, and it's correct because we always flush any translations that might be stale. We follow the same policy as the hardware TLB, and it's slow. So in software, we optimize things by saying we're going to save these translated these translated page tables, and then when the guest switches their fake CR3 from this table to this one, we're going to switch the real CR3 from, here we've got this correspondence. We're going to keep around the translated page table corresponding to each fake page table. But what that means is we have to make sure that we trap any modifications here. So in order to do this optimization where we don't throw away any translations, it means we have to write protect these page tables, or at least anything that we've translated into here, we have to write protect. So we don't necessarily need to know, we may not have to worry about the entire page table, but we have to worry about the parts that we've translated. And so those pages, we have to write protect them, and if the guest OS modifies them, we trap that modification and we perform the translated modification on the page table here. Or we invalidate the page table here and fault it back in. Either way, but we want to make sure that we there's a bunch of, at this point, there's a bunch of different ways we can do it. However, we have to make sure that we avoid inconsistency, that if there's a mapping in this table, there's either no mapping in this table or there's the correct mapping. We never want to have a case where this table contains an incorrect mapping. So that's why we put this write protection here. We put it on all of the guest OS's page tables, not just the active one, so that when it makes any modifications to them, we can update them. And as I said, this is an optimization because the translated addresses in these real page tables in the hypervisor are much more valuable than the translations in the TLB. There's a lot more of them, and it's much more expensive to translate each of them. so we can get higher efficiency by saving them. We introduce complexity by saving them. And unlike hardware, well, and it's much easier to deal with complexity in software, we do it by going and using tricks such as write protecting these and so on. So this is, you'll see if you look, there's several papers by VMware. There's an OSDI paper by Carl Waltzberger that this is referred to as a software TLB, and that's because it's essentially software managing translations from the guest operating system page tables to the real physical addresses. The last thing I wanted to mention as an example of is hypervisors have been used in a lot of security research. One of the more interesting ones is Overshadow. Chen, Garfinkel, and all, and this was ASPLOS 2008. And the idea here is to have a secure application on top of an untrusted OS with a trusted hypervisor underneath. So for instance, you could have a secure application running on top of Windows, and even if someone installed a rootkit here or something like that, they would have no way to actually access any data in this application or do anything except possibly kill the application and stop it from running. And the way this was done was basically that the application, it started up with what they called a shim, which was a small, so what was loaded by the untrusted OS was actually this small application which would allocate a bunch of memory and then directly communicate to the hypervisor using some type of exception mechanism, basically a hypercall, which would load the program up, the real application here, and then whenever we switch from this application to the guest OS, and remember, any such switch has to go through the hypervisor because we're switching to, the guest OS is running in supervisor mode, where it thinks it's running in supervisor mode. So to transition from emulated user mode to emulated supervisor mode, we have to go through the hypervisor. And when that happens, the hypervisor would encrypt this application. And then when it sees that it's switching back to the application, it first checks that it has a hash here to check whether the application had been corrupted, and if it has been, it'll kill it. Otherwise, it decrypts the application. So this untrusted operating system never sees the original code for the application because that got loaded in by the hypervisor when the OS wasn't looking, and it never sees the data or the code because that's only visible while this application is executing. I think this works best on a single processor system. So essentially you have your application. If time's going this way, we load from the hypervisor, and then we encrypt. And here we're running the guest OS. Here we might be running some other stuff. And then we decrypt, and we go back to running our app. We encrypt again. So in particular, this application is able to use the underlying OS. Clearly, if it's going to, well, we can do it in ways that that either transparently encrypt all the data, or other ways that don't encrypt it. But because, well, but as I said, no matter what the OS does, it can never actually subvert this application, because whenever because the hypervisor ensures that the application is protected, that it's cloaked whenever the guest OS is running, and that the application is only uncloaked whenever we've switched, the guest OS has stopped running and has started directly executing that our secure app. So in general, there's been a lot of work done on on security with virtual machines. There's various ways that you can use them to monitor an operating system from underneath and look at its behavior, see whether it's been subverted. In general, it's much more difficult to subvert a hypervisor than it is an operating system, because the services it provides are so much simpler. That doesn't mean that it's impossible. However, in general, there have been far fewer exploits. So with that, I guess that's about all we need to cover for virtualization in this class. I'll point out this has been a very active area of systems research since since the DISCO work from Rosenblum and Waltzberger. And through the 2000s, it was very active. It seems to be dying down now. I would say, in fact, that one of the reasons that it's been such an active area of work is because this is an area where it's very difficult to experiment radically with an existing operating system, especially if it's Windows, but even if it's Linux or one of the BSDs. They're very large. They're very, it's a lot of work to radically change them, and it's very unlikely that you'll get someone else to use it when you're done. However, the hypervisor lets you put another operating system layer underneath it, in which you can do all sorts of things that you may not be able to do without radical changes to the operating system. And you can do this in a way that it still runs the normal applications and so on. So to some extent, I think the popularity of virtualization research, and maybe some of its popularity in the market, is because it's an area, is because of the inertia of established operating systems, that you really can't change them very much, but if you can put a set of changes in underneath it transparently, then that has a lot of value. Okay.